Okay, so this is a math stack exchange or question about card shuffling, and someone talks about Shannon entropy here. In fact, that person talking about it is named, what's their name? Statra. So they wrote a computer program, and you can see, do you see the sum? Do you know that symbol that means sum? The probability times the log of the probability, just like we did.
Okay.
Okay. And we followed their procedure. Now, when they did it by a computer shuffle, they went from 0, a little bit below 1, a little bit above 1, to 2. It took them a while to get to 3, actually, using a computer shuffle.
And they sort of leveled off.
And then they leveled off between 3 and 3.5. And sometimes it went up, sometimes it went down. See that? Which is the same thing we found, by the way.
Yeah.
Yep.
Our Shannon entropy was at 5 was around, it was like 3.4, right? And then we went to 3.3, but it sort of levels off around there. Now, and then you can actually, he has these really cool charts that actually show the card distributions. So there's the original card distributions, 1 through 52.
Yep.
And what happens, why do you think that graph looks like that with that riffle shuffle?
Well, because you kind of take the two groups and kind of you make them like go together. So you have basically just the two groups.
Okay.
But in 3 it's the same.
What do you, can you give me an explanation here for what this looks like at number 3?
Well, then it's sort of the same thing that happens. You've got the two groups where you're splitting those two groups. But you can sort of see the dots now because there's not as many things in the groups.
Okay.
And then it starts to get more random.
Yeah, and then it starts to get more and more random. So it's actually pretty neat. Now, why do you think would be the possibility that hand shuffling rather than computer-generated shuffling might mix the cards up a little bit more quickly?
Well, computer shuffling might always do the same thing, and hand shuffling is different every time.
You might accidentally put a card, two cards might accidentally stick together.
Okay.
Those might be grouped together.
Right, so 2 cards might stick together. That would make it less random.
Yep.
And also, but you could, a normal riffle shuffle, you're supposed to take about half the deck, and the computer would take exactly half.
Okay.
But here you could take maybe only 24 cards instead of 26.
Okay. So it might and all right. So it might mix it up in slightly different ways every time. So you wouldn't get these perfect lines and stuff like that.
Yeah.
Also, the computer does perfect shuffles every time.
Yeah. So it's interesting. So I wouldn't count on us going from 0 to 1.5 to 3 as quickly as we did. In fact, it took the computer, looks like what, 8 times to get above 3.
To level off, yeah.
And then once they got above 3, yeah, you can see they leveled off pretty quickly, which is what we saw. Once we got above 3, we didn't change that much. But it's actually pretty neat. So you could, and there are lots of different ways to shuffle, actually, aren't there?
Yeah.
So you could actually study shuffling and find out which ways of shuffling mix up the cards the quickest. It would be actually a fun little project to do. But so anyway, just to wrap up. So this, when I mentioned we would do this yesterday, you thought there would be no way you could measure this randomness.
Yeah.
And it turns out there is, and it's a concept called entropy.
Yeah.
And we followed the procedure and found and got basically the same results that they found online.
It's cool.
Yeah, it's pretty cool, huh? All right, high five, guys. Good work.